and it gives us a way of calculating in particular the deflection that is experienced during by two compact objects during a collision, during a scattering process, simply by taking the derivative with respect to the impact parameter. And then, okay, we simply wrote down the known results that are actually well known since several decades for the leading and subleading. So 1 p.m. post-Minkowski and 2 p.m. Results for this quantity, and then towards the end we briefly flashed what happens at 3 p.m. Yeah. Although we will come back to this later in the lecture. So maybe while we still wait for the machine to cooperate, are there any questions? Please.
So these dots inside the bracket.
Yeah. These dots are the
huh?
first ones?
No, those. Yeah, those.
Yeah.
But the parameters expansion which controls the dots.
Yeah, still. Last time we introduced a name for these guys, but they will not play a very big role. So the reason why this big delta is surprised compared to this small delta is that given the relevant scales of the problems, so these two objects with masses in 1 and 2, for us being in the classical limit means that we are staying in a regime in which gm squared, or more precisely gm squared over h bar, is very big. This is what we mean by classical. This means these things are trans-Planckian objects in the sense that their mass is very heavy compared to the Planck mass, and big delta is suppressed by small delta by an inverse power of this guy. In fact, as a cute exercise, if you want to spend some time, you can plug in the values for typical masses, and you will find that this is very, very large, like 10 to the 79, 78.
Delta, small delta is dependent on h bar.
No, small delta is very big, so it's proportional to gm squared over h bar. And to leading order, it has a logarithmic dependence on this impact parameter. So the leading 1 p.m. deflection goes like 1 over b, just because you take the derivative. And then it receives corrections that are suppressed by the pm parameter. So the reason why the cross-perturbation theory in the classical sense, so this post-Minkowskian approximation, is that gm over b instead is a small parameter. So these corrections are sized by gm over b and then gm over b squared. So in fact the idea is that the exponent of this impact parameter representation has a nicer classical expansion, pm expansion than the amplitude, because of course if you re-expand everything in powers of g, you will find things that scale like 1 over h bar squared, etc., etc. So
it's like semi-classical expansion. You have a leading term 1 h bar, and then you have series and powers of h bar. Yeah.
Exactly. So these guys, for instance, will scale at one loop as gm over b squared or something like that. Enhancement. And of course, one could say, why don't you write them at the exponent? After all, it's your choice, coupling of things. And the reason why they don't matter for this for this equality, I should write here something like plus delta quantum. But okay, on one hand, they would be suppressed by this h bar over gm squared 10 to the minus 79, and on the other hand, to go from here to here, we employed a stationary phase approximation, which I mean is reliable only when the exponent is very large. So there is no strong reason to trust, I would say, this additional contribution. So yeah, maybe we still need to be a few more minutes.
You are online on YouTube. It's okay.
Okay, very good. Then we can start. So yeah, as a brief recall now offline, last time we discussed this diagonal exponentiation as a means of understanding the classical limit of the amplitude and extracting the deflection, which is in a sense a sort of bottom-up approach, right? We started by discussing the tree level, then the one loop, seeing how this exponentiation arises, and then eventually we provided this saddle point or stationary phase argument to calculate a physical observable, so in this case the deflection. Or impulse, or if you prefer the deflection angle, theta. Except this time we will discuss a different approach to calculate the same, eventually the same observable. So in particular we will reproduce this 1 p.m. and 2 p.m. results, in a different using a different strategy. So in a sense, instead this time it will be a top-down approach. So we will start by setting up the calculation following in particular the work of David Kosover, Ben Maybe, and Donald O'Connell. So in particular, maybe let me write down the reference in this case. And which is an observable-based formalism. So now instead of working our way to the calculation of the amplitude and then eventually arriving at an observable, we start just by setting up the problem. In particular, we will introduce two states that describe our initial incoming particles. So we will do so in a quantum mechanical spirit. So let me introduce some notation. Minus P1, introduce some wave packet describing particle 1, an exponential, and then the single particle momentum eigenstate, and similarly for particle 2, of course. Well, this notation is just a shorthand for the on-shell phase-space integration. Let me remind you that for historical reasons, I prefer working with these all outgoing conventions. So P1 and P2 are formally passed directly instead of being the physical momentum. This is the reason why there is this minus sign here. And so the idea is that the initial state will just be described by the tensor product of these two states, because in the far past these two particles are very far apart. They are just described by this structure here, and the impact parameter. Now the impact parameter associated to the initial state is just this B1 minus B2. So for me in particular, it points towards particle 1. Now the key idea is that we know how to relate the time evolution of this initial state to amplitude, because in a sense this is exactly what the S matrix is telling us. So there will be an out state, which is just the S matrix time acting on the initial state. And the idea is that if we are interested in a change of a physical observable during the scattering, or more precisely between the situation before the scattering and after the scattering, well, we can simply take expectation values. So in particular, suppose we're interested in some observable O in this expectation value in the final state, then we need to calculate something like this. Or if we want to calculate the variation of some observable before and after the scattering, of course we can calculate. And then, of course, we can expand out in terms of the S matrix in terms of 1 plus IT, and then we can relate this quantity to the T matrix element, which are our amplitudes. So in order, in fact, the objective of today's, let's say the first half of today's lecture is to apply this explicitly to the case of the impulse and see what happens. Now, in order to do that, let me introduce again some convenient notation, in particular some convenient choice of initial and final momentum variables. This is a bit boring, but just to be precise. So the idea is to introduce some sort of average or bright frame momenta, or bar variable. And the idea is that this is convenient. This is particularly convenient because then, using the mass shell conditions, you can show very easily that these are exactly orthogonal to the momentum transfer, essentially because the P1 and P4 have the same mass. And let me further introduce some sort of velocities U1 and U2 defined in such a way that U1 bar is M1 bar, is M2. These U1 and U2 are normalized to 1 or -1 in my signature. And just to complete all the invariants that enter, minus, so sigma minus q squared divided by m1 and 2, and then there is a factor of 4 divided by m1 bar into bar. So you remember the sigma parameter is what, well, as also Ricardo was complaining a little bit, rightly so, is what people usually would call gamma. So this is 1 minus v squared, and this is defined with respect to the initial velocity. So this is minus p1 dot p2 not barred divided by m1. Okay, so basically the idea is to rotate this, roughly speaking, a little bit in such a way that things become a little simpler later on. Okay, then another key statement that I will need, although I will show it in great detail, is the following. Suppose we are interested in some operator, and this will be the case in particular for the combinations that enter our expectation values later on, that satisfies this. So in a sense it's a elastic 2-to-2 operator. So there is some delta function and then the sum over all momenta times a function. Let me again, by slight abuse of notation, denote calligraphic O, which only depends on P1, P2, and Q being P1 plus P4. So this is a function again. Then what happens is that the sole role of this wave packet that we introduce at some point is essentially to introduce a Fourier transform of this O. So the statement is that in O in the classical limit for a classically well-defined observable, such as the momentum, or later on we will consider energy, angular momentum radiated by the field. This is just the Fourier transform of this form function O evaluated as B, more precisely Bj. And to leading order, you remember last time we introduced a distinction between the Fourier transform they call Ft and the one they call tilde. This is a distinction that is only relevant to subleading orders in the h bar expansion, so inverse powers of this h bar over, well, j in a sense. But since here we are focusing on classically well-defined observable and leading orders in the classical limit, here there will be no distinction. So this is the same as O tilde beta. Okay, this if you want, I leave it to you as an exercise. And it's crucial to use in this in showing this the fact that one is taking the classical limit and the wave packets are sharply peaked at the classical values that we want to use for our scattering, so in particular P1 and P2. Okay, so with this in mind, let's start. Let's try to apply this formula in the case of the test. Yeah.
So back in the previous lecture with Iconal, it was important that there is this distinction.
Yeah. And the reason was that we were dealing with slightly dangerous objects in a sense, which are the expansions of what, of course, I just erased. Things like delta 0 squared divided by h bar squared, so which involves a 1 over h bar squared, right? And then if you would modify this ft, you would generate some corrections that are of the form 1 plus h bar over pb squared times something. And then you see that this something could modify something that appears as subleading order. So in particular, in this case, it would only modify this big delta 1. So it would modify the quantum remainder, which in turn was important to calculate delta 2. So there's a whole song and dance.
It's the problem of calculating, let's say, the amplitude in this regime, but if we calculate it, we can just plug it in and in the formula.
Yes, it's important in the sense that if you, for instance, if you were to define the diagonal exponentiation in this way, delta prime 2 and delta prime 1 would be slightly different. So of course the amplitude would be the same, but since this object is a bit different, this sub-subleading object will be a bit different. Instead here, in the KMC approach, if you, the key point, as we will see shortly, will be the interference essentially between a couple of terms that enter this out-out piece, and those will already cancel whatever is the order 1 over h bar squared, and therefore the result will already be well defined and already classical, so you don't care about anything that is subleading. Yeah, it's a bit different, but eventually the two results will agree if I manage to get the calculation right. Okay, so maybe let's start with a fresh piece of chalk. Okay, so the idea is to apply this formula to the impulse. So our observable will be P1 mu, say the momentum of particle 1. And we will be interested in what we were calling Q mu, which is just delta P1. So we'll expand it in the same way as before. There will be a 1 p.m. and a 2 p.m. contribution. But we will calculate it from this. So using S equal to 1 plus IT, of course. Continue here. There will be an in term that cancels out. Then there is a minus I in dagger P1 plus I in P1 T, and then plus in T dagger P1 T E, right? So in fact, maybe let me try to do something potentially dangerous. Pull out this I. Okay. And then we will discuss this, the implications of this equation order by order in the loop expansion. So let's start by tree level, of course. Let me further erase. So tree level or leading order, or let's say order G. So to order G, we can simply neglect. So how is this thing to be interpreted? Of course, P1 measures the momentum of particle 1 in the incoming state here, in the bra associated to the incoming state hat here. Here, of course, in order to make sense of this relation, we need to insert some completeness relation, right? And then we will end up with some cut contribution. So for instance, leading order, we will have something that's in, so 1, 2, and then we will have a 2 particle cut corresponding to the other in, and then we could have also higher cuts, of course. So there is a sum over all these kind of contributions, measured, weighted by the momentum of the particle 1 in the cut. But to leading order, of course, all of these are higher orders in G, so we can just worry about these guys over here. So let me remind you, okay, here is the convention. So here we have U 1 PM is simply, let me remind you that the statement over there, so in eventually is just a Fourier transform, and then we need to apply the operator to the kinematics in this drawing. So maybe let me start from here. So P1 will pick up the momentum of particle in the final state, which is P4. And then we are left with the 2 to 2 amplitude. Fourier transform. And instead here, we pick up the physical momentum of particle 1 in the initial state, which is minus P1 because of this convention. And then we can simply put the 3-level amplitude because we are sticking to at 1 p.m. So now this is And then using the usual identities for the Fourier transform, we can also write this dTB Fourier transform of A0, but this is precisely the leading output, right? Okay, more precisely dJ. So we recover indeed the same result that we had last time, minus dj over b q1pm whose absolute value, let me remind you, is 4, 3, 1, 2 sigma squared minus 1/2 divided by b square root of sigma squared minus. Okay, so this was easy. Let's try to do something slightly less trivial. Go to the next order. Now, to go to the next order, not only we have to include the one loop amplitude contribution from here and from here, but now we start being sensitive to the first non-trivial cut here, which is in particular this two-particle cut, in which now the blobs are still a three-level amplitude, right? Because we have g times g, which is g squared, and is of the same order as the one loop amplitude here. So let's do that. So there is this I that I pull down, Fourier transform, and now we have, and you can start from this term, P4 now times the one loop amplitude, so A1, and then minus P1 again picks up a minus, so minus P1, so plus P1, and then there is again A1 but starred, right? Because it's okay, T dagger, as you know, definition of Hermitian conjugate. Then there is this minus I. And then let me be a bit more precise about the routing of the momenta in this cut here. So I'll call this P1, then I choose the loop momentum to flow clockwise, and then this is going to be L minus P1, this is going to be P4. So the momentum that is picked up by this P1 is L minus P1. And then we have to write the amplitude, which are three-level amplitudes, so now we don't care about star, non-star, they are just three-level amplitudes with momentum exchange L and Q minus L, or L minus Q, it doesn't matter. And then let me introduce a notation for this Lorentz invariant phase space, which in this case is simply takes into account the mass shell condition for the intermediate state, so L, and then there's 2 pi delta of 2 P1 dot L minus L squared, and the other guy is that have a plus. Okay. Very good. So now another piece of information that can be useful for us now is to remember that the amplitude satisfies unitarity. So S dagger S is equal to 1, and in particular this implies that this order that twice the imaginary parts of the one loop amplitude is given precisely by this cut, but without any weight. So this guy, let me not write it explicitly, literally this expression without, oops, without this guy over here. So we can use this to further simplify the expression. So in particular here we will have P1 plus P4 times the real part, right, which is insensitive to this star. And then we will have the imaginary part. So
sorry,
yep.
Don't you have a theta function thing?
Right, thanks for the question. Yes, I will need to include it. The reason why I did not include it is that in a second we will expand for L small. So let me say L will be small compared to P1 and P2. So it will never be big enough to make P1 minus P1 negative if it was positive to begin with. But thanks for the question. Yeah. So now here we have I times the imaginary part, so let's say plus I P4 I think imaginary part has a 1/2, right? Here instead we have minus I times the imaginary part, so minus 1/2. And then here there is an I, here there is a minus sign, which I do not forget. Okay, integrated against the 0L, d0 minus q, the Lorentz invariant phase space L. Please tell me if you see some signs that don't make sense, because otherwise. Very good. So let's simplify this a bit. This becomes 1/2 q, right? Because we have p1 plus p4 minus L mu. So let me write this expression in two pieces. The first one is the one involving the real part. So I ft of the real part of the one loop amplitude plus I, and let me call this whole thing with a name S, which is equal to dependent q, and this S is q mu minus L mu a0 and a0 to minus L. Okay. So let's discuss these two things separately. First, the easy piece, which is this guy. Oh, times q mu. I forgot. So for this guy, we can play exactly the same game that we played for the three-level case. So this is going to be the Fourier transform, the ddj of the Fourier transform of the real part of the one loop amplitude. But this is again exactly the iconal, or more precisely the next leading order contribution to the iconal, delta 1. So then we find minus bj times q2pm well, with the q2pm, the expression that you have in the notes for last time. Maybe, let me see if I've written it here somewhere. Yes. 3 pi t squared 1 and 2 and 1 plus and 2 divided by 4 times the famous 5 sigma squared minus 1. Okay. Now what about this additional piece, right? This guy with S. So for this piece we can try to play a game similar to the one we played last time when taking the Fourier transform of the convolution and trying to rewrite as the product of two Fourier transforms. So let's see how that goes. So to do that, now we will employ the approximation that we mentioned a minute ago. So you remember we are not interested in the full calculation of the one loop contribution to this guy, but only in the limit for large B, which in turn translates in the limit for small q, which by the method of regions translates to the limit of small l as well, because the soft region, the region in which L scales in the same way as q, is the relevant one of this process. We will see more in detail next time. So in practice, what this means is that we can expand this integrand for small l. And okay, the amplitude is actually homogeneous, so we don't need to expand it. They are already the correct one, provided that we only take this 1 over L squared pole, right? So we only need to expand this Lorentz invariant phase space. So let's do that. Particularly the delta functions are the non-trivial bit. You can show that they take this form. Where now I'm introducing this, using this p bar, which is useful and has been introduced earlier on. Here I think there is a minus. Yes. So we literally expand them in a Taylor series, nothing fancy. There will be a leading term. And then a subleading term which involves this L dot L minus Q. times, well, once we will pick up delta primes times delta, and the other time with a minus sign we will have to pick up delta times delta prime. And then there will be higher orders, which is we clear shortly don't actually matter for our case, for our calculation today. Very good. So let me try to discuss this. I mean, maybe it's a bit better use of my space on the blackboard if I don't rewrite this expression times this. You can imagine that now I substituted the delta functions here. Now the important bit, or maybe here if you prefer, the important bit is that this leading order contribution, when you multiply it by this structure, you can see that it is odd under L going to Q minus L. So contribute something odd. And the reason is that you remember Q now is exactly orthogonal to P1 bar and P2 bar, so this transformation doesn't do anything on these delta functions. Again, here is the bit where this P bar is useful because this condition is now exact, so we don't need to care about any feed down terms in this step. And instead, okay, the amplitudes are also invariant, right? Because they just go, well, they get swapped to one another. And instead, this structure is odd, so it picks up a minus sign. So by this step, we are sure that the integral of this is actually going to be 0. So we only need to care about the next leading bit. And to massage that, well, we are going to use the properties of the delta function, in particular the fact that delta prime to P1 dot L can be rewritten. I don't know if I already introduced these variables last time, but let me write down a reminder just in case. So in this term now, what we can do is that we can neglect subleading terms that come from the distinction between P1 bar and minus P1, right? So for instance, anything that is proportional to Q here, we can just disregard. So something like this. And whatever mistake we make, we go down in this dot to dot. And okay, we have to remember that delta prime of minus something is minus the delta prime of something, so which is what I'm writing here. And this V1 check and V2 check are defined with respect to the initial state. So V1 check, for instance, is sigma V2 minus V1 divided by sigma squared minus 1, which is simply defined in such a way that V1 check dot V1 is minus 1 and V1 check dot V2 is exactly 0. So they are sort of dual velocity. But this is just a technicality. The important bit is that you can use this identity to rewrite this as a derivative with respect to L mu or L rho, and then integrate by parts. So then IDP. And what happens when you integrate by parts is that you could either hit this guy, but you can easily check that this contribution vanishes thanks to the delta functions that now have been sort of freed from derivatives. Particularly, we'll pick up something that is killed by this guy. And similarly for when the derivative acts on the amplitude. So the only contribution that arises is when the derivative acts on this L hat. So let me write down the result. So the result is that there is the structuring process, as you can see, comes precisely from these guys, and the free index comes from this song and dance involving the partial integration, and then an integral. Or maybe let me first write it without the tilde, so the things before Fourier transform. and then these two. These two delta functions, but now when we take the Fourier transform, now we are in a position to apply the same trick that we applied last time. So this is manifestly a convolution now, and the Fourier transform of the convolution is indeed the product with the Fourier transform. So what we get is that the final result, now take into account both this piece and this piece, or its Fourier transform more precisely, is the following. So minus bj over b q2pm plus this combination times q1pm squared. And the reason why this is the case is obvious from here, right? Because each of these guys will be a Fourier transform of, say, q times the amplitude, but this is again the derivative of the of delta 0 in Fourier transform, which is the 1pm impulse. So this is just the square of the 2pm impulse, possibly up to sign. Okay. So in fact, now to comment on this result, let me do something that I hated when my teachers did that, which is to erase part of the equation that I already wrote and write the full impulse up to 2pm. Now plus dot. So this is our full result. With q1pm and q2pm written somewhere, either in your notes or on the blackboard, but that's not important. What I wanted to highlight is that if you now try to compare this expression with what we obtained last time, it seems to be different. Right? Last time we had something which was minus b mu over b times q1pm plus q2pm. This piece was nowhere to be seen. So what is going on? To make it even sharper, the problem, quote unquote, is that last time we had something like this. Maybe even more precise, plus order g cube. So this term cannot save us. So the reason why the two expressions seem different is that b and bj are not the same. So you remember one of the first drawings that we had on the blackboard was this this one. And this is what I'm calling B. Sometimes it's also called the iconal impact parameter, which is other. And instead, Bj here is defined with respect to the incoming state. So, and the two differ by a rotation of theta half at leading order in G. Otherwise, they also differ in the absolute value, because of course the absolute value of Bj must be equal to the absolute value of b times the cosine of theta half. But as you can see, this is an order G squared distinction, so it's not relevant for us today. The relevant bit is the rotation. So the precise relation between these two guys is precisely that b is equal to bj minus b1 check minus b2 check. B. To leading order, it doesn't matter if it's B or Bj, but this is actually B. You can show more generally for a generic elastic process, not necessarily a leading order in the PM expansion. So now you can see that if you substitute this, you precisely spawn this term from here. Now, of course, yeah, there is also the right minus sign from here that cancels and gives the plus. So as a sanity check, what we can check now, in order to verify that what we are doing is reasonably sensible, is to verify that this term is there precisely to make sure that this Q that we are adding to P1, so the deflection, stays on shell, right? So we can verify that p squared minus q1 squared should be equal to 0 up to order GQ corrections. So let's try to do that. Of course, there will be the m1 squared piece will cancel, and then there will be 2p1 dot q minus q squared. So in q squared, of course, if we only care about order g squared contributions, we can just stick to this guy squared. So this is going to be minus q squared 1pm plus order q. And now this guy over here is going to be 2p1, so 2. Then p1 is minus m1 times v minus v times v1 times v1 check is plus 1. So this is the size. Now the math is a bit quick done on the blackboard, but you can do it more easily at home, and this is indeed what you get. So this is correct as long as the variables involved in the expression are the ones sort of anchored to the incoming state. So if this is minus p1, this is m1 v1. And bj is the guy orthogonal to the incoming state. However, the result simplifies a little bit if we use this sort of average or iconal variable, so this b, and then, okay, it's sort of natural to define some p tilde 1 and p tilde 2, which are now exactly orthogonal to this guy, and we can write them down perhaps here. Just for future reference. They are basically related to P1 and P2 in the same way as the P bar variables, but there is an important distinction. Minus P tilde 2 plus minus half Q mu, and similarly for P3, P4. So the important distinction, you remember, is that instead the P bars here at small q. So while the bar variables differ from the incoming momenta due to order h bar corrections, so small momentum perturbative corrections, these instead differ by an order g meaning the leading impulse. So by a classical correction, which is small in the PM expansion, but is non-negligible if you go to subleading order. So the last remark before going on, as I was saying, to leading order, in particular the one relevant for this calculation that we discussed, this is just a rotation because you can neglect the difference between the absolute values of B and Bj, and in fact you can write it down formally as an operator. And there is both a piece that involves derivatives with respect to V and a piece which involves derivatives with respect to B. Bj. And you can check that indeed by acting with this operator on the leading order result, you generate this additional piece here. So you want minus S tilde is equal to Q1 PM times this operator acting on Q, again 1 PM. In particular, you can check that this is a well-defined operator in the sense that it preserves the constraints that B1 and Bj satisfy, so that the fact that they are orthogonal, and as a consequence of this, you can check that this equation holds. In a sense, no matter what representation of Q1 PM you use, you could use the explicit expression that we wrote at some point. So Bj divided by, well, Bj mu divided by B times Q, or its integral representation. It's kind of nice to see that given the two different representations, it seems that in one case only this piece matters, and in the other case only this piece matters. But the reason is that, of course, only the sum is a moving component. Okay, any questions?
Index, where's the index move?
Here probably. Yes, thanks. Okay, any question on this distinction? I mean, the reason why I want to do this in kind of detail is that we'll play a role also later on when we are going to discuss the waveform, hoping that we get there. So I wanted to highlight this distinction a little bit. Maybe before going to the break, let us now go back and ask ourselves, do we know that B is supposed to be B and not Bj in the iconal exponentiation, right? Because in a sense, up to now, this was a sort of prescription, which shows that everything works, in particular comparing these two methods. But is there an intrinsic way of seeing it? So one way, which was discussed in a particularly nice way in this paper here, 07556, by Andrea Cristofori, Riccardo Gonzo, Nathan Moynihan, Donald O'Connell, Ross, our Matteo Sergola here from IPhT, and Chris White, is to be a bit more careful about this step involving the saddle point or stationary phase conditions. You remember at some point in our discussion we said, but if the momentum, the impact parameter space amplitude has resummed in terms of this phase here, when we go back, we can use the saddle point approximation to say that the dominant contribution in the inverse Fourier transform would be given by the derivative. And this is of course correct, as we checked. But essentially the objective now is to make this even a bit more precise. So the idea is to combine the best of both worlds, so still use this incoming state that involves a clear definition of Bj, because it's clear that when you use the incoming momenta, incoming impact parameter in the two states, right, 1 and 2, they will be the incoming ones. And then try to apply the iconal exponentiation to the S matrix acting on this initial state. So now this initial state is the same that we discussed 50 minutes ago. And now we rewrite this by inserting a complete set of states. Then there are the exponentials. There we go. So this first piece is just the one involving P1 and P2 is just the definition of in. And instead, this P3, P4, P3, P4 insertion is the insertion of a complete set of free state. Yes, by the way, sorry. A comment that I would have liked to make, and then of course I forgot to make, in relation to Nicola's question earlier, was the fact that you remember at some point it was rather important that there was a piece involving, so in this KMOC story, there was the cancellation of a piece involving this delta P1 bar, delta P2 bar, times the amplitude and I think there was also L, well, a combination of L and Q, so roughly L, probably 1/2 Q minus L, something like this, integrated over the DL. And okay, let's try to see why it's important this bit cancels. So as a scaling, you remember L scales like Q, so these bits contribute to 1 over Q, 1 over Q, 1 over Q. Each of these amplitudes also contributes like 1 over Q squared. and the amplitude and the measure here contributes like 4 powers of q, right? When we are in 4 dimension, so we are left with this guy over here, which is another power of q. So now the Fourier transform, when we do also the Fourier transform, this involves 2 additional powers of q from the measure, right? It would be integral d dq, so d minus 2q, so d2q, and everything has to be translated to q being 1 over b, right? So if I can make mistakes, this would scale like 1 over b. And instead, the classical contribution to the impulse at 1 p.m. scales like 1 over b, but the classical contribution to the impulse at 2 p.m. should scale as 1 over b squared, right? So you see this. This is sometimes referred to as a classically singular or superclassical term. This would be the pieces analogous to delta 0 squared that appeared in the icona. So this classically singular bit, but the statement of the great observation by KMOC is that these potentially singular pieces cancel order by order in perturbation theory, and this is a manifestation of this cancellation. So this is the sense in which I was saying this is a classically well-defined observable. It's because these guys cancel out. Okay, let's go back to our iconal now.
Is it correct to say if it wouldn't cancel out, it would be not infrared safe?
Sorry?
If it wouldn't cancel out, it will not be infrared safe?
It would be not a classically well-defined observable. For instance, the number of emitted gravitons during the collision. So in a sense, yes. The 2 things are related, but yeah, I think there is a priori an expectation of what should be well-defined classically. Right? The total deflection, you just let the 2 things evolve, they just go in some separate ways. The solution will be a bit trickier for the waveform, because the waveform, as we will see, will be classical in the sense that these superclassical pieces cancel out, but it still has a, well, harmless, reasonably harmless infrared divergence, but we'll discuss it later. Any other question? Yeah.
Regarding this, so this should keep on at higher orders, also interference terms like delta and big delta.
Exactly. So also at 2 loops, for instance, the same happens, and also at 3 loops, this happens perfectly.
KMC, I directly get delta 0, delta 1, delta 2.
In a sense, this shows with KMOC you directly get the derivative of delta 1 divided by b mu, without having to worry about that in the amplitude there would have been a 2 delta 0 squared, because it cancels in this way. Okay. On the other hand, one could say that the icon is also nice because in that way you see that in the classical limit there is an exponentiation, and you see the fact that the interaction is mediated by many gravitons. Instead, here it's kind of hidden, right? Because you just, well, in the diagrams that you typically draw at 1 loop, you have at most 2 graviton exchanges or something like this, and eventually you get the right result of this order. But it seems a bit strange that you get the right classical result from just a couple of graviton exchanges, right? But the reason is precisely this. There is an explanation behind, but order by order in perturbation theory, it doesn't matter if you look at an observable. Okay, so massaging a bit this, let me not do it in detail, otherwise we have to skip the recreation. How do you say the pause? So we can massage this expression by shifting the momentum in such a way that the final result is the following. Let me write it down and then comment. There is this S, which we also introduced at some point in the first lecture. Now this is nothing but 1 plus I, the Fourier transform for A, J, and this Fourier transform can be conveniently written down, in particular now using these p tilde variables that we just introduced. So let me do that. dq, so now there is a d-dimensional integration times our familiar delta function, but which are conveniently written down in terms of these tilde variables, and the amplitude, and finally the exponential. This is a bit of an abuse of notation, right? Because q already appears in here, while the integration over q appears in the last factor, but I hope you can bear with me. Of course, all the integral signs should be at the beginning. I'm just highlighting this part because this will be relevant for these subtle point approximations. So now the idea is to use the icon exponentiation, but in reverse. So to use the fact that the amplitude exponentiate, and then we can inverse Fourier transform the B-space exponentiation by saying that this is equal to literally the inverse Fourier transform now with respect to an unconstrained variable x, b, sorry, okay, b, e to the minus I x dot q, where x is an unconstrained dimensional variable, but b is the projection of x orthogonal to p1 tilde and p2 tilde, and the reason why this is the case is that, well, the integration over x parallel 1 and x parallel 2, if you want, will be the ones reproducing the delta function that you see in the square bracket to p1 to t. Okay. So in this step, we believe the icon exponentiation and we use it. But now the saddle point step is going to be a bit more involved. And the reason is that, okay, now the object that we have to discuss at the end of the day is this ddq, ddx, and then there are two factors, e to the 2I delta coming from here. So the minus 1 cancels, by the way, right, in this because it's just a delta function. Times for minus I x minus bj dot q. And the idea now is that we should apply our stationary phase argument, but to this full integral, which, as you can see, is non-trivial both in x and in q. Let's see how this works. So, of course, there are two saddle point conditions. The first one is, let's say, with respect to x. This is the familiar one, right? Because it just tells us that this exponent should be stationary with respect to the gradient with respect to x mu, so we get just a q mu equal to derivative of delta in respect to x. And now we should be a bit more careful because b depends on x through this projection. So this is a little exercise I leave for you if you want to show that this is exactly what the derivative with respect to the argument, which is a scalar, times b mu divided by b. And this is, if you want, minus b mu divided by b times q, the absolute value of the momentum, and q is minus. The reason why there is a minus is that gravity is attractive. So for the explicit expression, this delta has, its derivative is negative, meaning that the momentum deflection of particle, say, 1 must point towards particle 2, not towards particle 1. So this is why this is positive. This is the positive quantity. Okay, so this is good. But the non-trivial part is the other one. So up to now we still don't know what B is.
Bj doesn't depend on x? J.
Sorry?
Bj. It also depends on x.
No, Bj is defined with respect to the incoming state. Is the one you remember in the definition of the wave packet. There were B1 and B2. Bj is just B1 minus B2, which are just parameters. Except B depends on x. Yeah, this is an important distinction. So let me do this and then we can take a break. So the other saddle point condition, saddle is with respect to q. So what we get by taking the derivative is that now x minus bj is given by the derivative of this delta with respect to q, which, okay, again, short exercise. You can massage it in a similar way. Ah, sorry, I shouldn't go there probably. So now the derivative of b with respect to q, and the reason why b depends on q is that b is the projection of x orthogonal to p1 tilde, p2 tilde, and p1 tilde, p2 tilde depend on q because they are, if you want, p4 minus 1/2 q and p3 plus 1/2 q or something like that. So now we have to take this into account.
Derivatives with respect to q nu.
Ah, sorry. One of the two must be a nu. That's this. I was worried that it would go in the shadow and then I got in the front. Okay, so the idea is to just write down the expansion. So x will be this b plus some decomposition. Let me write down in terms of p tilde and some coefficient to be fixed. Say p1 minus p2 and p1 plus p2 are two natural choices of vectors, right? Which we can also rewrite in terms of the final state plus k1 minus no plus p4 minus p3 minus q. These are just the definition of p1 tilde and p2 tilde. And now the idea is to take the derivative of this identity, keeping in mind that x and q are independent, right? So this means that we get 0 equals, say, dv tilde dq nu plus, and then here no dependence on, there is no dependence on q. Of course, a1 and a2 can depend on q, so there will be something like p3 plus p4 dA1 dq plus p4 minus p3 dA2 dq nu. And then, of course, the derivative can also hit the explicit q, so delta. Now there is a further trick. So when we substitute this relation here, we note that the upper index is always contracted with q. And this can be rewritten in terms of p1 tilde, p2 tilde. So these two are automatically orthogonal to q, so we don't care. The only bit that matters is this guy. So we end up with and you get the sign correct, probably plus. And now the idea is that you again substitute this relation, so this sort of ansatz, back in here. And now the magic should be that if I did everything correctly, the dependence on q should cancel. So x, here we have the chances that this sign is correct are basically very, very small. So, okay, let's try. So, b plus minus bj are equal to q a2. And now we have to remember that p1 tilde and p2 tilde are related to p1 and p2. Now we want to express things in terms of the incoming state. So this should be simply minus p1 plus p2. And now, okay, let me write it down. p1 is minus p tilde 1 plus 1/2 q, and p2 is minus p2 minus 1/2 q. So it seems we are in business. Now, of course, we get the sign of P1 and P2 wrong, but it doesn't really matter. The important bit is that we get a plus Q. And probably should have swapped the sign, right, of P1 and P2. But anyway, this doesn't matter. What this relation is telling us is that B is a linear combination. B differs from Bj, sorry, by a linear combination of P1 and P2 that doesn't involve Q. So now, one way you can solve this is now an easy exercise. You can just make the life easier. Instead of choosing P1 and P2, you can choose the famous V1 check and V2 check, and show that the relation is minus V1 check. So the one that we wrote earlier on the blackboard. You can fix this by imposing the orthogonality with respect to P1 tilde, P2 tilde. Times QB. Okay. So to conclude, let's check that the square of this satisfies the identity that we want. Okay, now we have shown in this subtle point way that the B appearing in the iconal exponentiation is not Bj, what the drawing was suggesting. Another property that we want is that when we square this, so let me bring this, let me square this. Now here there is a plus, and then these guys satisfy some. So that there is an overall 1 over sigma squared minus 1 that comes from the square of this B check. And then let me pull out another 1 over 4 and 1 and 2 that comes from the denominators. So this will be n1 squared plus n2 squared, sorry, 2 and 1 and 2 plus n2 squared times q squared b squared. So this we recognize as being the minus invariant S. And bringing it to the other side, we find that b squared times 1 minus, you remember there was this identity S, M1, M2 is equal to E, which is the square root of S times the momentum, P. So this is precisely 1 over 4P squared, Q squared, equal to Bj squared. But Q is also equal to 2P sine of theta over 2 in the center of mass frame. So this is precisely B cosine theta half equal to B. So the conclusion is that the drawing is correct. Okay, I think we can take a short break unless there are questions. Okay.
Then see us online if you have questions. You can speak.
Okay, then maybe we reconvene around 11:20, 22.
11:22. Okay, I'll write here. Okay.
Okay, before going to the next part, let me just make a brief parenthesis. So up to now we focus on this deflection angle, which is in essentially the most interesting observable that you can extract from the 2-to-2 elastic amplitude. In principle, a subtle point or stationary phase argument similar to the one that we discussed in order to go from impact parameter to momentum can also be applied to go from energy to time. And the result of the stationary phase approximation is a prediction for this time, which is a time delay. It's essentially the time delay that is experienced by the objects as each object as a consequence of the presence of the other one. And okay, the point why it is not really so interesting, especially in 4 dimensions, is that the derivative with respect to the energy does not have this nice property that we were saying. You remember that the derivative with respect to impact parameter cancels the infrared divergence appearing in delta 0 when, as you can see here, the derivative doesn't help you with this infrared divergence, which means that this time delay is formally infinite in 4 dimensions, or more precisely that the only observable things are differences of time delays for processes at different impact parameters. So if you want delta t, but in a sense this is more or less the same as the derivative with respect to the impact parameter, right? It's an infinitesimal difference. So it contains more or less the same information as the angle. Anyway, I wanted to write it down because it will be relevant later on. So okay, now let me go back to a topic that we have touched upon a couple of times already, and let me try to discuss in some generality in order to make things precise. So the initial statement will be very simple. So the S matrix is unitary. This translates to this pull out minus sign. This statement concerning the T matrix, so S plus B equals 1 plus IT. And then the idea is to extract information from this identity by taking matrix elements of this operator identity and inserting a complete set of states here. So let's take a sandwich between two states A and B. So here, of course, we get the matrix element for A going to B. And instead here we will get the star of the process for B going to A, right? Because of the rules of the dimensional conjugate. And in here, the insertion, let me use a sort of shorthand notation, sum over the intermediate state, which can be generic. And of course depend on the theory. The theory decides what processes are allowed, what intermediate processes are allowed. Say, of course here by stripping off an overall delta function we are restricting to PA plus PB equal to 0, so let's say PA plus P intermediate times the amplitude for A going to an intermediate state, sorry, I, times the star of the amplitude for B going to the intermediate state, right? Let me remind you. The definition. Okay. Now, in the rest, we will be interested in exploring what happens when this identity is applied in particular to the 2-to-2 amplitude. So this A and B will be just two particle states. And therefore here it's clear that the process A going to B or B going to A doesn't matter because for scalars, sorry, this is just a function of the two Mandelstam invariant S and T, which don't matter. It doesn't matter if you define with respect to incoming or the initial state. So what I'm trying to say is that here this is going to be minus I A of Q, our beloved 2-to-2 amplitude. So this is just twice the imaginary part. And then there will be this guy here. And then in principle you have to sum over all possible processes that link 1, 2 to 3, 4 with intermediate on-shell states. And in particular this will involve some okay, let me be a bit more precise, another step before the drawings. So then here we would again have this sum. And now here is a bit awkward because in our drawings we will be considering amplitudes that in which the A, so 1 and 2 goes to some intermediate state, and then we will draw the amplitude, the star of the amplitude for an intermediate state going to B, not for B going to an intermediate state. So the reason why this is going to be correct in this lecture is that we will be focused on scalars minimally coupled to gravity, and in particular what can be shown using CPT is that this is the same as in general, this is the same as the amplitude for the intermediate state CPT conjugate going to the B state CPT conjugate, but for our state the CPT conjugate will not matter. So I can be more precise about this, but this is not the idea. Of course, when this is a 2-to-2 case, you can reapply the same argument you have here. It doesn't matter if the in state or the out state are swapped. For the gravity of final state, it could be a bit more puzzling, but this is the reason. So here we could include some 2-particle state, 3-particle state, and then in particular we would include more. But for today we will stop there. So what I will do is I will write this as twice the imaginary part, 2-particle channel, plus twice the imaginary part, 3 particle channel, and so on. Okay, let's start from the 2 particle channel. Evidently simple. So this is very similar to what we already applied for this KMOC style calculation of the impulse. So twice the imaginary part in the 2 particle channel is just given by the integral in this Lorentz invariant phase space with 2 particles. Maybe let me use Q1 for the loop momentum. Q1 A, Q1 minus Q, star. And the idea will be to try to translate this into statements in impact parameter space. So up to here, this was completely standard material. You can find it in any textbook. What is slightly less familiar, perhaps, is how to apply this machinery to obtain predictions and constraints that apply to our B-space impact parameter space problem. So the idea will be to play by now, but at the end of the course, you will be extremely familiar with the idea of taking Fourier transform of convolutions and transforming them in products of Fourier transform. This is essentially all we are going to do. So the idea is again to try to apply the Fourier transform and try to massage this in order to factorize it as much as possible. So let me maybe write it down at least once in full glory. So there is the Lorentz invariant phase space delta functions. Let me write it down exactly, except for the fact that I'm not including the theta functions, because eventually these Q1s and Q will be small. But at the moment, let me write them to all orders. Times K of Q1 minus Q squared plus Q squared A of Q minus Q1 star times Very good. So now, again, the idea is to try to change variable in such a way to factorize this thing. Let me try Q going to Q1 plus Q1 prime and see what happens. So here we don't have to do anything. So if I was on my iPad, I could copy this here, but I can do that now. Try to be quick. This is not an advertisement for the iPad. Okay, now the interesting part of the game is to see what happens here, right? So let me take this guy, for instance. So we have 2p1.q, which is q1 plus q1 prime, minus q squared, which is q1 squared, minus 2q1.q1 prime plus, minus q1 prime squared. And now the trick is that we are going to use the delta function sitting upstairs to deduce that this is equal. So you see in particular this p1.q and this q1 squared, we can cancel them. And what we can do is we can collect the q1 and the p1. So 2p1 minus q1 dot q1 prime minus q1 prime squared. And the same you can check happens for the other guy. So we have a e to the I p dot q1 plus q1 squared amplitude calculated in q1 prime e to the I b dot q1 prime. Okay. So now you see what happened, that this expression has almost factorized, right? And the reason is that here it's a prime. And the reason is that the Fourier transform is formally the same in both lines. But what happened is that the Fourier transform in the second line is defined with respect to the on-shell moment of the intermediate particles. So this is minus p1 plus q1, right? Whereas the one in the first line is well, of course, defined with respect to the incoming state of the initial process, the initial state. So what we can do is we can write this in this almost factorized form, in which I specify with the subscript what the Fourier transform is performed, so the argument with respect to which we are performing the Fourier transform. This is equal to ft of q1 aq1 of ft q1 prime of aq1 prime, but calculated with p replaced by p1 minus q1 and p2 replaced by p2 plus q2. Right. If there was no distinction here, then it would be exactly factorized, but this is not the case. So as you will see, this will not be a huge problem because we can expand. But I wanted to make this inference very sharp because it's going to be important in the next lecture. So now what we can do is to apply this to our case, well, to the case at hand. For instance, when we focus, what happens when we focus on a three-level amplitude of the form? Well, okay, first there is an obvious consequence that we can deduce at the very beginning, namely if we just care about this identity at order g, what happens is that here this is going to be a three-level amplitude, and of course here we cannot put anything because, well, this would be at least order g squared, so we immediately deduce that there is no imaginary part for the three-level amplitude, which is, of course, known, and neither there is in impact parameters. Of course, a trivial consequence is that the leading iconal, there is no imaginary part. Now let's see what happens if we apply this identity by putting the three-level amplitude on the right-hand side. This will give us an imaginary part for the one loop, something we discussed also last time. So let me write this schematically as a0 divided by q squared, where a0 more precisely is, for our case, 32 pi g and 1 squared. And then there is no denominator, I don't know why. Okay. So what happens in this case is that you remember, since here we have a 1 over q squared, now really the distinction between the ft and the tilde Fourier transform is negligible. You can look back at an expression that I gave last time, but the reason is that whenever you try to expand these delta functions with respect to their q squared, you will get something that cancels the 1 over q squared that is here, so this doesn't matter. The point that does matter is, however, this lack of factorization. So what you can do is you can first perform the Fourier transform that is inside here, so when q is replaced by q1 prime, and this will be exactly the same as the delta 0 we calculated in the first lecture, except that you have to replace things appropriately. So let me write it down. Sorry, q1, of course, in that case. So what we're going to get is the usual iconal for EP, A0, for pi, gamma minus epsilon, pi squared, B squared, minus epsilon, except now here B is not the impact parameter orthogonal to P1 and P2, but the impact parameter orthogonal to P1 prime and P2 prime, this P1 minus Q. So let me denote it by B prime of Q1, where B prime is orthogonal to P1 prime and P2 prime. Okay, then it's an exercise very similar to the one we sketched in the previous lecture to show that this orthogonal projection takes the form b prime mu equals b mu plus v1 prime check times b dot q1, where v prime are defined with respect to the p prime, of course. So now what you have to do is that you have to substitute this inside this expression and multiply it by another 3-level amplitude. And now here you can expand this the square of this b prime, which is b squared plus something of order b times q squared, right? So let me not do the steps in detail, but the bottom line is that the twice the imaginary part now of the one loop amplitude, or the Fourier transform, sorry, of the one loop amplitude. So when we apply this formula using this trick here, it will be, of course, the 3-level amplitude square. So to leading order, it is true that the thing factorizes, right? Because to leading order, you can just neglect this q1, q2, sorry, q1 plus q1 and minus q1 here, and then it really becomes the product of the two Fourier transforms and the factor of 1/2. So let me write it this way. And then there is a subleading piece, which is related to what earlier we were calling the quantum remainder, right? Two epsilon, and then there is a function. Managed to squeeze it in here. 43 0 over 4 pi gamma of minus epsilon of 1 minus epsilon divided by pi minus epsilon squared. Sorry if this is not readable, please tell me. Anyway, plus higher order corrections. So as you can see, delta 0 scales like logarithm of b, or if you prefer, it doesn't scale with b. This scales like 1 over b squared. So as promised, this is an order h bar over pb squared correction with respect to the leading order. So this is a quantum correction in this sense. And then there will be, of course, subleading terms if you were to expand further this denominator. But okay. So the reason why I went in detail through this is that earlier, so in the previous lecture, we saw that to leading order, indeed the unitarity relation is factorized for the 2-to-2 channel by going to impact parameter space. And this is true, but only to leading order. To subleading order, you have to take care of this sort of a slight lack of factorization. So there is an additional contribution which is not exactly factorized, but okay. This is due to the simplification of going to impact parameter space, and just to anticipate a bit, not going to proper angular momentum variables, which of course instead would exactly diagonalize the 2-to-2 contributions to the sorry, the two particle channel contributions to the unitarity relation, but this we will see next time. Okay, now instead what I wanted to do is to apply this this thing to deduce something about also the subleading iconals. So let's do that. So from here we see that this, whatever this is, we will mix just with this quantum remainder. Let me recall the form of the iconal exponentiation. Just to and then for later this 2. Okay. So now what I'm trying to say is that this beast here will only contribute to this quantum remainder here, because it's suppressed by 2 powers of inverse powers of b with respect to the leading order. So from that relation we can deduce that there is no contribution to delta 1, right? So imaginary part of delta 1 is real. Sorry, is 0. Delta 1 is real. Is this step clear? More or less. now let's try to go to the next order. So to do that, let me write this relation in a simplified form, which is enough for our purposes. So now let me not care about this lack of factorization and write the following. So imaginary part, twice imaginary part of a particle cut is equal to so this would be, if we apply this relation, we neglect this lack of factorization, which only enters at next to leading order, and we also neglect the distinction between ft and tilde, because it also enters at next to leading order. So these are all subtleties that are washed away in the classical limit. So let me remind ourselves of this fact. This lack of factorization is there, but is sub-leading. So now the idea is to insert the icon exponentiation in both sides of this relation. So in particular, well, the more general form is this one. So of course, to leading order, what we recover is that the imaginary part of delta 0 is 0. To next leading order, we recover the imaginary part of delta 1 is 0, but then we get also a statement about the next leading order. So in particular, that the imaginary part of given by the two particle cut to a tilde 2, the two loop amplitude. Okay, there is a bit of algebra, but it's very easy. You just have to expand this guy and evaluate the absolute value square. Of course, whatever remains must be real because it's an absolute value square. And you get the following. So of course this is a schematic, it's not actually one. And now the idea is to compare this statement with the form of the icon exponentiation at two loops. As you can see from here, there are a couple of pieces that match, right? So there is this 2 delta 0, delta 1 is exactly the same. So remember we have to strip one I because there is an explicit I here, and then take the imaginary part, so we strip another I. So this is exactly the same. And then also from here, right? The imaginary part, the contribution to the imaginary part will come from when this is stripped off because of that I, and then there is a real part here. So this is precisely this guy. So the conclusions are, there are two possible conclusions. The first one is that delta 1 is real. And by the way, this guy only contributes to the real part, so that's why it doesn't appear there. So now what we are trying to do is to conclude something about the imaginary part of delta 2, right? So there are two possibilities, either that it is real, or that it has an imaginary part, but then it cannot come from the two particle cut, right? And the reason is that, okay, as you can see from this check, the imaginary part coming from the two particle cut is exhausted by the icon exponentiation itself. So it is already given by these two pieces. So what we can conclude in other words is that the imaginary part given by the two particle cut of delta 2 is 0. So now our next task is to discuss the three particle cut. So and by the way, the reason why we didn't discuss the three particle cut for the one loop amplitude is that, of course, it's prohibited by power count, right? You cannot receive any contribution G square. The amplitude cannot receive any inelastic contribution at G square for this gravity theory. It can only enter at G cube, as will be clear shortly. Any question on this part? Okay. So now three particle cut. Let me start by writing it down. The imaginary part of the three particle cut. Now, essentially, the drawing that we have in mind is this one, right? So we need a new ingredient, which is this 2 to 3 amplitude that up to now we never introduced. So let me define a notation for it. This guy is a function of the initial momenta, and then there are the kinematics is a bit richer, right? Because we have P1, P4, but now the sum is not just equal to minus P3, P2, there is also K, so I will define Q1 by P1 plus P4, Q2 by P3 plus P2, and Q1 plus Q2 plus K is 0 by momentum conservation. Okay. And then I often I will use a shorthand notation for the, especially in the classical limit again, I will suppress the dependence on P1 and P2. Just P1 and Q2 or P1 and K. Okay, so this is the object. So, some notation for the intermediate 3-particle phase space. A particular here we will, sorry. I guess we will stick just to the contribution to the 2-loop amplitude. So when this guy is a 3-level 3 amplitude. Well, now is that P1 and so yeah, maybe let me not introduce P4 and P3 here just yet. Let's say that they are really Q1 minus P1 in order to not generate confusion. I mean, these are morally correct when you just look at the 2 to 3 process, but now we are inserting it in a 2 to 2 process in which P4 is the final state of the 2 to 2 process, the overall thing, right? And okay, this relative line phase space in the classical limit simply given by the momentum phase space for the graviton. Now the theta function is important, and the other ones. So for the 2 massive lines, right? So Q1 minus P1 and Q2 minus P2, but we can solve Q2 to be minus Q1 minus K. So then this becomes, this is to leading order in the classical and soft limits or near forward limits. Okay. Yeah.
But taking a step back, so basically now you're checking the 3-particle cut because you want to understand whether the additional term cancels out with a contribution from here.
Yeah, what we want to do is to see if delta 2 can acquire an imaginary part or not. Okay. Because at 3 level, okay, of course there is none. At 1 loop, there was none, but it was not completely trivial, right? It was cancelling against the one coming from the iconal exponentiation, and then there was none for the iconal phase itself. And now we are trying to see if a similar mechanism happens also at 2 loops, so that eventually this delta 2 is just a phase, or if there is an imaginary part. Now we check that there is no imaginary part coming from the 2-particle cut. Yes. So now we have to calculate the 3-particle cut and see if it's non-trivial. But of course it will be, because here this thing is non-zero. But yes.
But isn't there like a difference in terms of the coupling? Because like with 3-particle cut, you have one more coupling constant basically.
Yes, exactly. So that's what. Thanks. I was almost forgetting. So from here it's clear by power counting this 2 leading orders case like order G cubed, because well, each of these guys case like order G to the 3/2. Instead the 3-level amplitude for the 2 to 2 process was scaling like G to the 1. Yeah. So that's the reason why the 2-particle cut already starts at 1 loop. Yeah. Instead, as you can see from the drawing, the 3-particle cut starts at 2 loops, so G cubed.
By checking the delta 2 contribution, do you know a priori whether it has like order G cube or G
cube, because it's 2 loop.
Okay.
So that's the right order that we are going to check.
Okay.
Yeah. Very good. So of course the calculation now starts to become a bit longer. I won't be able to do many of them on the blackboard except for these nice sort of song and dance concerning the interchanges of Fourier transform and convolutions. But the key idea is again Okay, let me give a couple of more details. So what do I mean by this notation? Of course, this is a thing which has indices. So we will work with a convenient representation of A0 which satisfies the word identity on head, of course. And then you remember, in principle here we are supposed to insert a complete set of states, so sum over the polarizations that are involved in the two possible eliciting of the gravitons that are appear as intermediate states, but this we can rewrite in terms of a polarization sum, which involves the TT projector, but as long as the amplitude that contracts this TT projector satisfies the word identity, we can trade it for the constant structure P mu rho sigma that we defined last time, but this is basically eta mu rho eta mu sigma plus minus d minus q eta mu mu eta rho sigma. Okay, so this is what I mean. I mean that they are always contracted in this way, if I don't say anything. And I think that's it. So now we will try to play our favorite game. And take the Fourier transform. So by now you know the drill, right? We're going to apply the Fourier transform to both sides and then try to come up with a change of variable. So, okay, this integral over k is just the measure with respect to k, and then we have our integrals. Then a bit delta 2 p1 dot q, etc., etc. Let me not do all the steps again because otherwise it gets really boring. Again, the idea will be that the right change of variable will be q going to q1 instead of q minus q1. This is the case now is a bit trickier because now it matters if the argument of a0 is q minus q1 or q1 minus q, because now there is no longer this symmetry. But what you can do by using this trick is to rewrite this as follows. Q1 plus k e to the I b dot q1 k, and then if you do things correctly, you will find that there is an identical structure just with the opposite sign in the exponent, and since the level amplitude is real, this is just the absolute value squared. So this, you remember that the usual story has been the fact that the Fourier transform of the convolution is the product of two Fourier transforms. Now this is interesting because it gives us a natural notion, the natural definition of the Fourier transform of the 2 to 3 amplitude, right? So this is the new ingredient. In fact, in order to make it completely symmetric, we will also include an ingredient that is not obvious from this, which is a phase. Of course, a pure phase goes away, but the way in which we define the Fourier transform of the 2 to 3 amplitude is the following. So I've introduced Q2, which had been solved in terms of Q1 plus K here, but it's kind of nicer to write it in a symmetric form. And then this phase I was talking about is well, let me be, since I still have some space, completely explicit. There we go. So you see here, if you want to solve, eventually x1 and x2 will be identified with b1 and b2 here, but here in this exponent you will get something which is and therefore if you solve q2 in terms of minus q1 minus k, you will get b dot q1 minus I say b2 dot k, right? But this phase doesn't depend on q1 and q2, is not integrated, sorry, on q1, and therefore it simply would go away in this value. But it's important in order to make sure that this transforms, for instance, in the right way under translation, right? You can check that if you shift then the will transform as e to the minus I a dot k. Very good. So finally, our result, then we can almost call it a day, is that the twice the imaginary part given that I have 3 particle cut of this a tilde, 2, is the integral over the momentum space of the gravitons of the Fourier transform of the 2 to 3, and then we suppress x1 and x2 or b1 and b2 for the moment. Very good. So this is clearly non-zero. In particular, it allows us to deduce that this is going to be the imaginary part of delta 2. What we learn is that indeed delta 2 does receive an imaginary part, and it's given by the first dissipative information that we encounter, right? It's given by the cut that involves a graviton, a non-shell graviton. So now, what I would love to do is to solve this for you explicitly, but this is very complicated. In fact, in this case, a more clever strategy is to actually go back, stay in momentum space, and then use our techniques, some techniques that we will discuss also a bit next time, to solve the integrals, the loop integrals in momentum space, and then take the Fourier transform at the very end, instead of going through this. First take the Fourier transform, and then try to integrate over k. And the reason is that this a tilde 0, as we will see in the last lecture, is related to the 3-level waveform, which is rather complicated in momentum space and in frequency domain. In fact, Filippo here had figure on that calculating it explicitly, but there is a leftover integral over parametric representations of Bessel function, which is rather involved. So it's better to invert the logic that we try to apply today. If one really wants to calculate it for generic, in full generality, what we will try to do in like 10 minutes that we have left is to instead try to calculate just one specific contribution to this, which is the divergent part. So IR divergent part. And as we will see shortly, this arises from the soft limit of this a tilde 0. So meaning k goes to 0. If you want, the regime in which the frequency, this k mu is some frequency times a unit vector, the limit in which omega times b over the velocity is much smaller than 1. So let me try to discuss this. So first statement is that in this limit, the amplitude simplifies considerably, thanks to the Weinberg subtheorem. So the 2 to 3 amplitude is given by a factor where the sum runs over 1, 2, 3, and 4. Times the 2 to 2 amplitude without graviton, so pictorially And now the idea is to split this integration into two pieces, one which collects the contribution from the soft gravitons, and the other ones which are instead non-soft contributions. So we introduce a cutoff simply, which is some intermediate scale between this and 1. And in this contribution we can apply this approximation, the Weinberg. There's a nice paper on 64 and another one in 65. And okay, the key simplification is the following, that as you can see from here, all the dependence on k is factorized in this simple form. And in fact, it's easy to check that the integral will be infrared divergent, and this is why we get this infrared divergence. Second, in principle, the way in which I should apply this rule, this equation, is that, remember, we are staying in the regime in which q is small. So in particular here, P4 will be equal to q minus q1, etc., etc. And I will need to expand for small q in order to get to retain only the contribution to which I am sensitive. But let me delay this and then expand. But let me delay this. It's actually easier to work with this for generic P1, P2, P3, P4, and then only at the end expand. The only thing that will happen is that eventually this will be proportional to Q. I mean, clearly this sum, if P1 and P2 are equal to minus P1 and minus P4, this sum is 0, right? Because it can be written as a sum over initial minus final state. So clearly it must be proportional to Q. And the only way this will enter eventually is the Fourier transform. Well, it's going to be the usual identity, Fourier transform of everything. From here will just come a power of Q. And this is our beloved Q1PM. So, but this we will do later, just a bit easier. So what we have to do is that we have to insert this guy here and take the contractions according to this summation rule. So we have to contract everything with this P mu nu rho sigma. So let's do it. So of course there are some kinematic factors. One is that is 1/2 from here. Then there is this 8 pi g, come from the square of the soft factor. Then there is a sum over A and B. We have two of these sums. And then the contractions will generate either PA dot PB squared or minus 1/2 the masses squared. Divided by PA dot K, PB dot K. And then the integral over K with some cutoff. Let me denote it with a theta function. So omega star being the cutoff scale and K0. So this is the type of integral you have to evaluate, and you can actually do it very easily. In fact, you can see all the dependence on K is in these denominators. There is, as promised, a contribution. So let me sketch how I evaluate the integral. The contribution from the frequency. You can divide the integration into frequency and angles, of course. So from the frequency, you just get an integral. So here we have dk divided by these guys and multiplied by the theta, by the delta function, right? So it will be an integral of d omega over omega to 1 plus 2 epsilon. The reason that dk as you can see has 4 d minus 2 minus 1 minus 1, so d minus 4. So of course I got it wrong. Does anybody see where the extra 1 over omega comes from? Ah, yes, thanks, because there is another omega, yes, because of course I should also count the omega, thanks for a moment. And then, okay, the cutoff, so omega star. And, okay, this is, as promised, this will give the infrared divergence, right? And instead, the integrals with respect to the angles can be evaluated straightforwardly. You can either exploit the fact that you know that the result will be Lorentz invariant and go to a frame, for instance, in which PA is at rest, or you can do it in a brute force way. But eventually the result is the following. And these are this is arc cosh of some parameter sigma that I will define in a second, where tangent MA and B, where sigma is defined like this. Okay, and eta is defined in such a way that it's plus for outgoing state and minus for incoming state. Okay, sorry, it was a lot all at once, but the bottom line is that this integral is easy to solve. I'll let you fill in the details since we are at the end of our allotted time. But let me try to conclude, wrap up with a punchline and a puzzle. So the punchline is that indeed this calculation captures the infrared divergent part that comes from that 1 over epsilon over there. Let me write it like this: 2 epsilon plus log omega star, which will be that cutoff over there. Of course, it would be omega star to the minus 2 epsilon, then we expand for small epsilon. And then there is a big factor of yeah, the remaining factors are just given by the kinematic factor and this arc cosh. So okay, let me write it down. Eta. And then you remember, in principle, we are supposed to expand. So remember this step that I sort of skipped over. Eventually, we are supposed to expand for small q in order to get the order g square contribution. And this is, okay, we give something proportional to q1pm squared and some function calligraphic I is a function of sigma. Let me not write too much in detail here. Okay, this is a function that we already defined in the first lecture, by the way. So the final result will be this times g over 4 pi times minus 1 over epsilon plus something that now I'm going to discuss. So the issue is what to do with this cutoff. So in principle, the calculation only predicts the divergent part. Of course, we can assign a meaning to this cutoff by saying that, well, the natural estimate for this by dimensional analysis is simply going to be the logarithm of the velocity, right? Because this would be omega times b in order to make it dimensionless. And you remember the regime of validity of this expansion was precisely when this is the frequency, when this is the velocity, so sigma squared minus 1. So this is the way to guess the right log, and indeed this is the correct result. You can check it. The method I was mentioning a few seconds ago. So this is the contribution to the imaginary part of delta 2, where the minus 1 over epsilon and this log, meaning the log that has a branch cut for sigma tends to 1, are reliable. And then there is a further trick you can apply. By unitarity, you can argue that the log must come from this combination here, minus I0, and therefore you can get a prediction not only for the log, so from the log you can get a prediction also about the factor of pi coming in the real part, right? Because if this appears in the imaginary part, I times pi will now contribute to the real part. And you can check that this is precisely the radiation reaction contribution that we mentioned last time. So this is precisely the real part to delta 2 radiation reaction. which precisely is G over 4 Q 1 pm squared times this calligraphic icon. Okay. Finally, a puzzle, and then we can really do lunch. Sorry for keeping you so long. We started a few minutes late. So, the puzzle is the following. You remember in the fact that there was this radiation reaction part in the iconal, in the real part of delta 2, together with the potential contribution, was important in particular because then when going to the large sigma limit, the arc cosh of sigma that appears in this calligraphic I was cancelling another piece appearing in the real part of delta 2. So this was important for sigma tends to infinity in particular. And it was in fact instrumental in making it well behaved as sigma tends to infinity. However, by a similar argument to what we just calculated, we remember, anticipating a bit, we remember that this E0 is the tree-level amplitude, so we can use it. We can use its absolute value squared as a sort of phase-space distribution of emitted gravitons. So in particular, if this absolute value squared, and also the reason why it's infrared divergent, by the way, is because it's basically the number of emitted gravitons in the process. Now, what happens if we multiply this by the frequency of each graviton? Well, we get an estimate of the total energy that is emitted due to soft gravitons, right? Okay, if you redo the same calculation and multiply by omega, what happens is that simply you don't have that infrared divergence, right? Because the omega cancels out. And there is another factor, because there is a 2 epsilon instead of an epsilon, so okay, there is a factor of 4 in total. So the statement is that the estimate of the energy, or the portion of the energy spectrum that comes from the so-called zero frequency limit, at order GQ, okay, is the limit at epsilon goes to 0. It's just a convenient way in order not to repeat formulas, minus 4 epsilon. And therefore, in particular, it's proportional to that calligraphic I of sigma. Now, the puzzle is the following. So this is literally the amount of energy that is carried away by soft gravitons in the frequency being, say, from 0 to 1 over b. So now if we multiply this by 1 over b in order to get the total energy emitted from this beam, we get the following. Now you see here we have a theta g times q squared, and then if you multiply by another delta omega of order 1 over b, you get another g over b. So this eventually is proportional to theta cube. So you see g cube at least is the right one, and the b brings out the correct factors of e and b. And then there is this logarithm of sigma that comes from here for large sigma. So this seems to mean that the energy that is emitted by the process, even just looking at the energy that is emitted by a soft graviton, is very, very big, not only, but it's arbitrarily large, right? Because you remember, theta 1 pm is of order G over B, and can be kept fixed and small in the high energy limit. So in particular, its cube will be similarly behaved, but sigma can be dialed up as much as you want. So it means that the total fraction of energy can even exceed 1, can be as large as you want. So this is clearly a nonsensical conclusion. And this is the first signal of this bound that I was hinting at in the first lecture. So it so happens that for some observables, it is not true that just by calculating a fixed order in G and dialing up the energy as much as you want, you get the right result for the massless case. In particular, okay, just to spoil a bit the conclusion, the right thing to do will be to calculate this object independently of the Tm expansion, just using the soft theorem, and without re-expanding in this way. And then we will see that the conclusion here is that this case is theta 1 pm log theta. So the reason why some observables are not well behaved is that they are not analytic in the coupling. And I think for today, I can stop here. Thank you. Any questions?
You said in the first part of your lecture, this pulse was proportional to the derivative of the economic phase. The fraction. Now if n phase is imaginary part.
Yeah, exactly.
What does it mean?
Yeah, the right thing to do is to discard it, and the reason, the simple-minded reason for this is that the imaginary part does not intervene in the stationary phase argument. After all, it sits in a real prefactor. So the right thing is to simply disregard it, and this indeed gives the right prediction for the angle at 3 p.m. So you include this real part coming from this analyticity argument, but you do not include the infrared divergent imaginary part. Again, another way of seeing this, the right thing to do is to go through the KMOC strategy, and there you can see that it simply drops out because of the KMOC cut. So this is another confirmation this is correct. And yet another way to see it is to go to what we will introduce later as the Eichhorn operator, which is essentially a refined way of redoing the calculation we did earlier, including both the initial state and the resummation in a sort of combined way. But that involves adding an additional operator degree of freedom in the exponent. So the idea is to take seriously the fact that the imaginary part appearing here is telling you that your Eichhorn exponentiation is not taking into account the additional inelastic channel that is there, because you are insisting on just trying to exponentiate the 2 to 2 amplitude, which is incomplete. So the idea is to build an operator that remembers, and the coefficient sitting in front of A and A dagger is precisely this A tilde 5-point amplitude. This will be this sketch in the next lecture.
And you just mentioned the very end that you have this paradox, what you mentioned, the paradox is also related to the fact that you truncated conventional economic phase finite number of terms.
Exactly. Precisely. So what one would need to do in order to recover this log is to resum the PM expansion, or the delta zero that one, and then eventually expand for small g over b. Now, a way out here is offered by the soft theorem, which is valid independently of the PM expansion. So literally, you can just take this formula, first expand for large sigma, and then expand for small deflections, and then you will find this formula correct. So the mistake is indeed restricting to a fixed order in the PM expansion. More precisely, there is a bound that tells you that sigma can be large at a given order in the PM expansion, but should not be larger than 1 over theta squared, if you want to do things really perturbatively for all observables. Then some other observables seem to be nicer, and they just work.
More questions? Okay, if not, thank Carlo.